So for this exercise, the hint was to rewrite this tangent cubed as tangent squared times tangent. So in a way that we can use the trigonometric identity, secant squared minus 1. So let me write it down. So tangent squared, and that's what I will replace all this with. Okay, so from here, well, the trick here is to distribute. So that's going to be the integral of secant squared tangent x dx minus the integral of tangent x dx. Alright, the thing is that if we distribute it this way and we wrote these two factors in the order that you're seeing on the screen, secant squared times tangent, maybe it's not so straightforward to see which one is the u and which one is the du part. However, if I rewrite the order of these two factors here instead as a tangent times secant squared, that's minus the integral of tangent. In this case, well, we can see, it's easier to see that tangent is the u, and the du part, it's secant squared x dx. Alright? So, yeah, this for this particular examples, this is a good example to illustrate how in many situations, how do we see the factors, which order of the factors gives us a better visual on how to set up the u du part. Alright, so let's go back to, okay, so that's the integral of u du minus the integral of tangent, and that integral of tangent is one of those formulas that we had above on the definition box. That's, well, number one, the integral of u is u squared over 2, and the integral of tangent is ln of secant plus c. But of course, let's go back, substitute for tangent. All right. Questions about this one? Let's have a look at letter B. And letter B, I'm not gonna lie, this one, when I remember when I took this class, I gave it a few tries. I gave it many different ways, and I end up again in some sort of in an infinite loop, going around in circles, getting nowhere, and then until I found out that this is one of those problems in which we need integration by parts, but also that special case of integration by parts in which we need to treat the problem like an equation, because after doing the integration by parts, the original problem comes again, and well, doing the integration by parts again and just going in circles, well, no, that's not how. So secant cubed theta d theta, so let's split this one into the integral of secant times secant squared theta d theta. And well, we split it this way so we can see which one is going to be our u du. In this case, well, I don't think the Liate is going to help us very well. Yes, okay, L logarithms, no logarithmic functions. I inverse trigonometric, no. A algebraic functions, no, we don't have any. T, trigonometric function. Well, that comes first. So that's going to be our U. But wait a minute. We have two factors, right, of trigonometric functions. Which one do we take for U and which one do we take for the du? Well, in this case, take the du part as the one that is easiest to integrate. In this case, between secant and secant squared, which one is easiest to integrate? The secant squared, because that's the integral for that is tangent. Otherwise, I mean, of course, you can integrate the secant, but I think that's ln of secant plus tangent that gets more complicated. So in this case, u equals to secant du, secant tangent, and the dv will be secant squared, and v will be tangent. That means go back to the original problem. Use the integration by parts formula, u times v, which is secant tangent, minus the integral of v, which is tangent, du, which is secant tangent. All right. Okay, so in this case, so v du, okay, yes, that's great. All right. So let's multiply these two tangents to get, okay, because I already mentioned that this problem will be treated like an equation, like the integrals that we did yesterday. I'm going to keep writing this in like if we were working on an equation. And in fact, we are working on an equation. So, well, this is going to be tangent times tangent. So that's, well, number one, secant tangent minus the integral of tangent theta squared secant. Now, why am I doing this and why am I not taking advantage of this? Well, in this case, there's nothing we can do. Yes, we see that secant tangent, but that secant tangent right here would be useful if this one were instead a secant, all right? Because the derivative of secant is secant tangent. We would have gotten just secant squared as the integral, but unfortunately it's not the case. That's not a secant, it's a tangent. So we need to rewrite this tangent in terms of secant using the trig identity that we already use. This one will be replaced with secant squared minus 1 that's a secant theta tangent theta minus the integral of secant squared x, oh not x actually, theta minus 1 and, well, let's distribute that secant. And I think from here you can see where we're going, where we're heading to. So this will be secant minus the integral secant cubed minus the, or rather plus the integral of secant. Alright, and that equals to the integral of secant d theta. Alright, what do we have over here? Isn't it the original problem again? Should we do another integration by parts and then keep adding more terms and never ending the problem? Well, no. Treat this like an equation. So add the integral of secant cube And on the one hand, cancel these two. And what's 1 plus 1? 2. 2 times the integral of secant cubed theta d theta equals secant theta tangent theta, and then plus the integral of secant theta d theta. And well, of course, we can divide both sides by 2 at this point and then just take care of this integral. Why not? So divide by 2, divide the whole thing by 2. And the integral of secant cubed will be equal to 1/2 secant tangent plus 1/2 the integral of secant. But what's the integral of secant? Secant plus tangent. And then plus c. All right. Yes, Anna?
Wouldn't the integral of secant theta d theta be negative? Because when you distributed it,
this one right here. So, well, this one is this negative right here, and then this negative times this negative becomes a positive. All right? You're welcome. So, yes. Note, if you want to write this as a note, why not? Treat it like an equation. Also, the integral of cosecant, it will be the same for the cosecant as well. I mean, because they're, they're co-functions, and also they will be behaving in a very similar way. All right, so let's see what else do we have. Well, let me have the whole thing zoomed out in case you missed anything, in case you have any question about this exercise. Okay, let's see what's next. All right, so notice for these problems we pretty much look at exercises involving tangents and secants. Of course, I mean, we can run into integrals that contain cotangents and cosecants, and well, for integrals for which we had 10 powers of tangents and powers of secants, we relied on this identity, the one that says 1 plus tangent squared equals to secant squared. And in an analogical way, well, we're using the corresponding trigonometric identity for involving cosecants and cotangents. In the same way, for powers of cotangents and cosecants, we would be relying on this trigonometric identity that involves cotangents and cosecants. And well, let me show you some sort of a little trick here, because well, sometimes those two trigonometric identities are not very easy to memorize. It's very easy to mess up a sign or the order of the term. So, but ultimately, everything, all these three identities stem from sine squared x plus cosine squared x equals to 1. I'm going to write it twice. And well, on the first case, I'm going to divide both sides by sine squared rather. Okay, what do we get? Sine squared over sine squared, that's just 1. Cosine squared over sine squared. Well, what's cosine over sine? Cotangent. And well, it's squared. And what's 1 over sine? Cosecant, but squared. And that's one way to derive the other identity. By, on the one hand, dividing by just sine, and on the other hand, guess what I'm going to do? Divide by cosine. So what's sine over cos? Tangent, but because in this case we have a power 2, that's tangent squared. What's cosine over cosine? Cancel. Plus 1. And what's 1 over cosine? Secant. And that's where these other two trigonometric identities are coming from. In case, sometimes memorizing things, again, you're running a risk or messing up a sign or the order of the terms. But the only one identity you need to know to get the other two is the basic sine squared plus cosine squared. On the one hand, get the other one by dividing by sine squared, and get the last one by dividing by cosine squared. Okay? So let's see, what's next? So for the next topic, or the next example, these are trigonometric identities, or trigonometric integrals, in which we will need to use the product to some identities. Some identities that these are covered in a pre-calculus course. I remember these are the last identities they covered. And well, in this case, we use these identities to evaluate integrals like the one that we have here, for example, number 4. And well, we have the integral of 6x cosine 13 over theta cosine 13 theta with respect theta. Well, so let's see. Yes, we have a sine and we also have a cosine, so we can think that we have a u du setup. All right, like u equals sine 6x du equals 6 cosine 6x dx. But wait a minute, when we try to compare this with what we have on our integrand, yes, we have a cosine function, don't we? But what's different in this case?
They have
different angles, right? They have different angles. If these were 6 theta also, perfect. U du, general power rule, and we're done. However, no, we need to work with this function first. So it's not going to work like this. And well, there's 3 identities to choose from. When we have a product of sine and a cosine with different angles, a product of 2 sines with different angles, and a product of 2 cosines with different angles. In this case, well, for our problem, it looks like the first identity is going to work. All right, so let's identify A and B in the first place. So for here, A equals to 6 theta and B equals to 13 theta. So let's use the trigonometric identity. So let's integrate 1/2 of sine of A plus B. In this case, that is 6 theta plus 13 theta, plus sine A minus B, that is 6 theta minus 13 theta with respect theta. So that's what we will do first. Okay, let's combine like terms. 6 plus 13, 6 minus 13. Doesn't look like anything impossible. However, the tricky part right here will be, okay, so that sine, well, let me keep it brackets. That sine 6 plus 13, is that a 19? Plus sine 6 minus 13, is that a negative 7? Negative 7 theta. D theta. Alright. You could do these 2 integrals. Okay, let me split them. That's 1/2 the integral of sine 19 theta d theta plus 1/2 sine integral sine negative 7 theta d theta. Yes, I mean, you can do this integral with a negative angle. However, how about taking advantage of a very important property of trigonometric functions? And you might remember the even odd properties for trigonometric functions. Well, let me list them real quick. Okay, let me list all of them. I think it's good review to list all of them. Okay, so that's sine negative theta, cosine tangent, that's cotangent, okay, what are each function equals to? So sine of a negative angle, what is that equal to? Well, another way to see these even odd properties, even and odd, that's also another way, a more colloquial way to see this is spit and swallow. So it turns out that the even ones swallow the negative sign, while the odd ones spit the negative sign. And from trigonometry, the only trigonometric functions that are even, another way to say even function, they are symmetric about the y-axis. Which function is that? Well, there's actually two, but let's start with only one. Which trigonometric function is symmetric about the y-axis? Cosine, right? So cosine, and of course its inverse, which is, oh no, not its inverse, it's reciprocal, secant. So the cosine function will just swallow the negative sign as well as the secant. The other function, the functions that are odd functions, spit the negative sign. All right. So this is something from trigonometry. How do we deal with trigonometric functions with negative angles? Because typically it's weird to work with negative angles. So instead, do whatever necessary with the negative sign on the angle by taking advantage of those even and odd properties. So in this case, okay, coming back to the original integral, what's going to happen with this negative 7 theta? So that negative right here will go outside as negative. Okay, let me erase all this. Never mind, I can't erase. So rewriting this integral, we will get, so 1/2 sine 19 theta minus 1/2 the integral sine 7 theta. And well, the integral of sine, what's the integral of sine? Negative cosine, so negative cosine 19 theta, and minus, well, plus rather, because minus will become a plus, cosine 7 theta plus c. But in this case we're missing those factors that come from the u substitution. Number one, okay, That'll be a 1 over 19, but that 1 over 19 times this 1/2, isn't that 1 over 38? And 1 over 7 times 1/2, isn't that 1 over 14? And that's our final answer here.